Hello and welcome to the ProgMath Multiplier event that took place in London in October 2021. So, a few things that we are going to take you through today. We're going to talk about the origin of the project. We are going to introduce the participants in the project, its aims, a few of the outcomes, and maybe discuss a little bit about what the future has in store. So, let's try and answer the question, what is really this project called ProgMath? First of all, everything started in 2015, where a collaborative European inquiry into technology enhanced into mathematical pedagogy started in the city of Västerås in Sweden. This was the first project that had to do with the introduction of technology alongside the teaching of mathematics. It was supported by the European Commission and the Erasmus Plus program. The countries that participated back then were Sweden, Romania, and the UK. Because of this collaboration that was really successful, a second project came along. So we have a new project and new partners. So the new project is called ProgMath, and its aim was to bring together programming and mathematics as part of the teaching of mathematics. So the partners were Sweden, Finland, France, Romania, and United Kingdom, and you can see all the participating schools. Associated partners were, among others, the University of Uppsala, the European Network of Social Authorities, as well as the regional office in Brussels, Belgium. So, the project really aims to contribute towards the development of teaching of mathematics in the classroom, address the need for integration of programming in the teaching of mathematics, provide teachers with educational support material, methods, and tools. The final and most important aim of the project was to actually increase the student engagement and interest in their own math classes, simply because we thought that programming and mathematics, first of all, go really well together and will make the lessons a bit more interesting than the current, more traditional teaching. Each partner worked in triads, so we collaboratively discussed and designed lessons, and we also collaborated with one of the other teams to produce another series of lessons. To present those, we participated either online or in person in meetings, shared our work, and prepared for the next phases of the project. Let's have a look at the individual meetings and events. So 6 transnational project meetings happened, 3 were face-to-face and 3 happened online. On the left, the first meeting that started it all was in Västerås in October 2018, followed by London in March of 2019, and in Botoșani, Romania in October 2019. Online meetings happened in Toulouse in March 2020, in Vosa in October 2020, and the final one was meant to happen in Brussels in October 2021. Let's have a look at some of the outputs from the project. First of all, we created a website, a web page that contains the details of the project, the model lessons, the online course, research, as well as other useful links. On the website, linked at the top, and you will find it together with the presentation of this video. You will find all the information that you need regarding the project. You will find the actual lessons and the recipe cards, and you will also find the online course that has a few examples and some walkthrough videos for Scratch, Python, and C++. For this final part of the presentation, let's have a look at some of the practical aspects of the lessons that we have made. So what we have here is a short showcase of one of our lessons. This particular one has to do with the application of matrices in solving simultaneous equations. This is an interactive Python notebook, and this is currently working through Google Colab. This is the notebook our students would typically get during that particular lesson. You can find this lesson linked with all the others on the recipe cards on our website. So this particular lesson is split into 3 sections. The first one introduces and lets the students explore a little bit the Python library SymPy. And then the following 2 sections are concerned about representing first and solving a 2x2 system of simultaneous equations in matrix form, and then extends that to the 3x3 case for the final one. So in the first section, the students will discover a few things about the library SymPy and a few bits and bobs. So they will learn how to define a matrix, for example, when it's given as a list of lists, or when it's given with dimensions first and then an ordered list. They will learn how to find the identity matrix of a 3x3 dimension, and then they will learn how to perform some elementary operations: addition, multiplication by a constant, and then addition, multiplication, power of a matrix, joining rows, using variables, substituting a number for that variable that they've just introduced, finding determinants, and finally finding the inverse of a matrix. Encourage them to take notes, because these are the commands they're going to have to fall back to for the remainder of the lesson. Once you've gone through the SymPy tutorial, now is the time for students to move on to the main part of the lesson, where they have to learn how to cast the system of 2 equations by 2 unknowns in matrix form. A particular example is given to them to guide them through this, and there are also questions that will prompt them to do exactly that in Python. The 3 commands here being pre-filled by us. In the original lesson, feel free to not have them at all and prompt the students to use the commands they just learned. So let's have a look. What is it asking? It's asking us to define the matrix A, the coefficient matrix, calculate the determinant, and finally compute the inverse. Encourage them, depending on the knowledge that they already have, to actually double check those calculations also by hand and see that they actually work in the same way. The next part just asks them to define the right-hand side. And then the final part shows them how to find the solution by multiplying the inverse of matrix A, the coefficient matrix that they just defined in the previous part, by the left-hand side column vector B. So magically they should get this solution here, 5, -2. So in this next part we look at the geometry of 2 different systems and how that links with the algebra and the coefficient matrices itself. So for this particular example, we have a system here where the 2 lines are parallel, and the system here where the 2 lines are actually coincident. So first thing we want our students to do is try and visualize the situation by calling a GeoGebra applet from within the notebook. Here, for example, they could type in the equations of the 2 lines, and see that for the first one they will get 2 parallel lines, like that. If they now change the second equation to what's given in the second system, they will realize that these two equations actually describe the same line, and therefore the two equations correspond to coincident lines that describe exactly the same line. So this is an introduction to infinitely many or no solutions given a particular system of simultaneous equations. The next part prompts them to consider the two coefficient matrices and discover, using the determinant, what this really means, because they know, or they should discover now, that when the determinant is 0, the coefficient matrix is singular, and therefore there will be no inverse exists, and therefore no unique solution to the system. In this last part, we introduce a parameter, the parameter k, and we're going to use exactly the same procedure, but now everything will be in terms of k and m, and we're going to use that as plenty of opportunity to discuss the geometry as well as the mathematics behind it. We're going to talk about consistency of the systems. Okay, so now here we have defined coefficient matrix and left hand side. Here we show them how to define the augmented matrix, and finally a short exercise for them to find the inverse in terms of k and state the values for which the inverse will not exist. So they have to think about the determinant or the denominators here and state that when k is negative 3/2, then the matrix is not invertible. A simple substitution in the next part. What happens when k is 5 and m is 21? The system has a unique solution. And then we go on and ask them what happens when k is negative 3/2, so when the original matrix is not invertible. So then that will lead on to a nice discussion and nice exploration about what happens geometrically as well as algebraically with the matrix. In this last and final section, the students get to explore the 3x3 case, where they have a 3x3 system to solve, represented by a 3x3 coefficient matrix and a 3x1 right-hand side vector. They will use exactly the same procedure as before, but they will now extend it to 3 dimensions. They will also see the geometry of this, and they will explore the relative positions of the 3 planes in 3 dimensions through GeoGebra in the various cases that arise. Well, that is about it. That was a really short showcase of one of our lessons. Thank you very much for listening.